Hello everyone and welcome to this video. Today I'm going to spend 3 minutes talking about an innovative and novel way to compress the haptic data and reduce the transmission rate. An example of a teleoperation system, which is the base of this thesis, is described in this figure. In this teleoperation architecture, the user controls the teleoperator by sending position and velocity commands through the network. The sensed haptic signals, for example 4 samples, are then transmitted back to the user and displayed to the user, forming a closed loop. Normally, haptic signals need to be updated at 1000 Hz to ensure perception experience, and that normally means a fairly high traffic load. One of the main ways that we compress the haptic data is called the deadband approach. We create a deadband for every transmitted sample, which is illustrated here as a blue region here on this picture. The next samples falling into the blue zone are considered to have too small intensity changes to be perceived by the user, and are therefore not transmitted. The deadband usually owns a static parameter which decides how big that blue region expands. One of the drawbacks of this compression type is the bursty traffic would take place frequently. We'll illustrate this effect by recording the packet transmission of different haptic interaction behaviors. The time periods with dense packet transmission imply bursty haptic traffic, and that is definitely something that we would like to avoid, because such transmission pattern would pose huge stress on the network channel. In our paper, we innovatively alter the deadband parameter, which is the size of the blue region. We expand the deadband when the algorithm identifies an increase in the packet rate, and vice versa. It can not only reduce the packet rate, but also mitigate the burstiness of the haptic traffic, while still maintain high user perception. Another aspect that we laid our eyes on is the rate control algorithm. As we all know, too high a packet rate can introduce communication unreliability if the required network resources are beyond the available channel capacity. In order to prevent such fluctuations, the packet rate must be limited. To this end, we propose a rate control algorithm which adaptively alters the deadband parameter to ensure that the mean packet rate is controlled stably around the target rate. The correlation between the deadband parameter and the mean packet rate could be described using a 4-parameter logistic curve and logistic regression, which enable us to fit the stats in a real-time scenario even with very few samples. In this experiment, the target mean packet rate is set to 175 packets per second. Compared with the original deadband approach without packet rate control, the proposed scheme constantly adjusts the deadband parameter to maintain a relatively smooth packet rate. I'd like to thank you for listening, and please feel free to check out my paper if you're interested in this topic.